Hello everyone, I'm Tianyuan from Hong Kong University of Science and Technology. Today I will present GREYHOUND, hunting file slows in hybrid parallel training at scale. This is the joint work with Alibaba Group. It tackles a critical yet often overlooked problem in large-scale AI training, the elusive file slow incidents, also known as the straggler problems. Here's today's roadmap. First, we will briefly introduce the background about the reliability issues in large-scale training. Second, we will explore the characteristics of the stragglers at scale, including their occurrence frequencies, root causes, and end-to-end impacts to the large-scale training. Then we will dive into the GREYHOUND design, including how to detect stragglers rapidly and how to mitigate them effectively. Finally, we will show some evaluation results to validate our system's performance. We start with the backgrounds. Large models are growing exponentially, from Bird's 340 million parameters in 2019 to today's multi-trillion parameter genes like GPT-4 or Llama 3. Model size have surged 30,000 times in just 6 years. Training these genes models requires massive clusters with thousands to tens of thousands of GPUs, running for weeks or months. To handle this, parallelism strategies evolved rapidly, from simple data parallelism to sophisticated hybrid approaches. Hybrid parallelism is the backbone of efficient large model training. Let's recap their basic characteristics. First, tensor parallelism or TP partitions layer computation to multiple compute devices. Second, data parallelism or DP creates multiple model replicas and shares data across these replicas. Third, pipeline parallelism or PP splits model layers into multiple PP stages. And as many other sophisticated parallelism like the context parallel and expert parallel are also evolving rapidly. Overall, modern large models are trained in a hybrid parallel manner, which combines these methods to optimize the resource use. But at this hyperscale, failures become the norm rather than exception. With thousands of GPUs running continuously, hardware degradation, software bugs, and network contention are guaranteed. What's worse, the sophisticated parallel strategies create frequent synchronization barriers. As a result, if any component fails stop, the whole system crashes. And if any component slows down, the whole system waits. Fail stop failures are the known devil, which cause complete system halts. For example, the OPT training is conducted on 1,000 GPUs and suffers from more than 100 crashes in 2 months. The Llama 3 training has a larger scale of 16,000 GPUs, but suffers from more than 400 failures in 54 days. The root causes of these failures span hardware faults, network errors, and software bugs. The community have developed many effective solutions, such as writing checkpoints with Checkfreak or Gemini, leveraging internal redundancy like using Recycle or Bamboo, or introducing elastic frameworks like OBlack. But this is only half of the story. Now we will introduce the hidden enemy, the file slow or stragglers, where components still functioning but degraded, such as the GPU throttled by overheating or network link congested by background traffic. Critically, even one straggler can slow down thousands of GPUs due to frequent synchronizations. Despite their prevalence and impacts, stragglers remain poorly understood and largely unaddressed. This gap is where GREYHOUND steps in. Now let's answer the first critical question: how do stragglers manifest at scale? We conducted an extensive characterization study in Alibaba's production cluster. Our study ran in Alibaba's multi-tenant HiPi cluster, which contains more than 10,000 of GPUs, including more than 1,000 H800s and over 2,000 of A100 and many other types of GPUs. The compute nodes are interconnected via high-speed Rocky V2 network in this spin-leaf topology, providing for 400 gigabytes link for each 800 node and for 200 gigabytes link for each A100 node. The cluster runs diverse workloads, including LM training, which is the majority, and LM inference, and recommendation model training and inference tasks. We use 2 approaches to draw the characteristics of stragglers. The first is cluster sampling. We repeatedly submitted over 400 single-node Type A probing jobs to detect computation stragglers and 107 4-node Type B jobs to detect communication stragglers. The second method is trace inspection. We manually analyze logs of 27 large jobs that each requires more than 512 nodes, GPUs. This gives us both macroscopic and macroscopic views. Here is an overview of our key findings. First, from cluster sampling, we found that computation stragglers are less frequent with only 1.5%, and probability and their impact is relatively low. On contrast, communication stragglers are more frequent and have higher impact to training. Second, analysis of the large-scale training jobs indicates that straggler jobs do have large impacts, which average duration is over 1 hour and can slow down the training by 34% in average. In summary, stragglers are transient, frequent, and can cause significant slowdowns. Now we dive deeper into the root causes. First, we introduce the computation stragglers caused by CPU contention. This occurs occasionally with about only 1% probability. In this case, multiple co-located jobs contend for host CPUs. As shown in this figure, where background jobs spec the training job's CPU satisfaction rate drops and will spend more time on CPU operations. This leads to about 20% throughput job and synchronized GPU utilization jobs. Although this contention is typically short-lived and within 10 minutes, it highlights the risks caused by multi-tenancy. Second, we show another type of computation straggler, which is caused by GPU thermal throttling. The occurrence probability is only about 0.5%. In this case, if one GPU, for example, the GPU 0 in this figure, hits the temperature threshold, throttling will be triggered, and it will be slowed down by about 20%. Then the synchronization operation causes all GPU utilization jobs simultaneously. These events are also brief in about 10 minutes, but indicate the hardware vulnerabilities. Then we will introduce the communication stragglers, where network congestion dominates these failures. We found that over 40% of 4-node probing jobs are affected, and the average duration is about 24 minutes. As shown in this figure, with the number about congestion increases, training performance drops sharply. We also found that internode RDMA links showed the highest variance compared to intranode NVLink or PCIEs, making them vulnerable to congestion. However, isolation remains challenging due to the spin-leaf network topology. Finally, we will show some case studies of stragglers at large scale. At hybrid scale with more than 1,000 GPUs, impacts are amplified. We found that about 60% of large jobs are affected by stragglers in their life cycle, and the average duration prolongs to about 72 minutes. Also, we found some catastrophic compound failures in large-scale jobs. As illustrated here, network congestion plus GPU throttling cuts throughput to only about 10% of normal. Okay, to summarize, stragglers are transient, mainly caused by computation degradation due to CPU contention or slow GPUs, and slow communication due to network congestion. Computation stragglers are short-lived, less frequent, while communication stragglers are more frequent and last a longer time, causing more significant degradation to end-to-end performance. Large-scale training experienced both computation and communication stragglers, causing significant throughput loss, potentially exceeding 90%. Having characterized the straggler problem, we now address our next critical problem. How can we detect straggler rapidly? To achieve this, a detection system must meet the following key requirements. A detection system must be first non-intrusive and framework transparent, requiring no code changes to the training framework. Second, it should be rapid and accurate, with minimal detection latency and near-zero false positives. Third, it should be fully automated, requiring zero human intervention. And fourth, it should be lightweight, only introducing minimal overhead to the original training job, and these principles guided our design. As illustrated in this figure, Greyhound uses the master worker architecture, enabling framework-agnostic detection in 3 phases: tracking, profiling, and validation. Workers are co-located with training processes, deploy lightweight training monitors that hook NICU calls via LD preload of the Linux system. Monitoring the communication operation calls, in the tracking phase, the local analyzers influences the iteration time without framework barriers and detect performance anomalies. When suspected slowdowns are identified, Greyhound enters the profiling mode, where the master coordinates a lightweight profiling to find a collective communication group that may contain struggling GPUs or links. Finally, Greyhound enters the validation mode. The master node briefly pauses the training and initiates lightweight validation benchmarks within these suspective communication groups to accurately locate the struggling component. In this talk, we focus on two core technique challenges. The challenge one is how to infer the iteration time without framework cooperation. And challenge two is to detect straggler onset and termination while distinguish them between the performance jitters. And challenge 3 and 4 is about the profiling and validation, which are detailed in our paper but omitted here due to the time limits. First, we focused on inference iteration time without framework knowledge. The insight is training iteration exhibit periodic communication patterns. For example, reduce scatter, all gather, and 2-hour reduces per iteration in this figure. Based on this insight, our solution is first hook the Nico cost and log the operation time and time steps. Then, we apply time series analysis techniques to identify the repeating parallels. Finally, we can get the iteration time between identical operations across consecutive parallels. For example, the iteration time here is T5 minus T1, okay? Then we use the Bayesian online change point detection algorithm to determine the onset and termination of a straggler event. We track the run length, which is the number of iterations since the last anomaly, and calculates the probability of slowdown at this iteration via the following equation, okay? And we flex a change point if the calculated slowdown probability is over 90%. But the raw BOCD algorithm has false positives. Our innovation here is to add a verification pass that only confirms the slowdown if iteration time jumps over a threshold. To summarize, Greyhound detect tracks Nico operations via the LD preload to infer iteration time in a non-intrusive way. Then it leverages BOCD plus verification to flag slowdowns. Later phases like the profiling and validation further pinpoint the exact straggler positions, such as GPUs or links, within several seconds. We've seen how to detect stragglers. Now we focus on how to mitigate them effectively. Greyhound mitigate takes the 3 core requirements. Mitigate system must be first reactive instead of predictive, since the straggler durations are unpredictable. Second, it should be online adjustable, requiring minimal job starts, and third, versatile. We should be able to handle both computation and communication stragglers. Now, checkpoint and restart is too heavy, ignoring is too risky. We need an adaptive middle ground. We first explore the design space, including 4 strategies. S1 is to ignore, it has 0 cost yet 0 gain. S2 is to adjust macro batch distribution across data parallel groups, rebalancing the workloads and for the slow DP groups. It has a low cost but only effective for computation stragglers. S3 is to adjust parallelism and topology. The key insight here is data parallel communication is more sensitive to congestion than pipeline parallel. This is due to DP requires more communication volume to all reduce the gradients. Thus, we can reassign the healthy links for heavy DP traffic and use the congested link for lightweight PP communication. This method has a medium cost. S4 is to perform checkpoint and restart. This ultimately eliminates fail slow by isolating slow components, but has the highest cost. The key challenge is the optimal strategy depends on straggler impacts and duration, which cannot be known in parallel. Fortunately, we can formulate as a classic online decision problem, like the ski rental dilemma. A skier goes to a ski resort with 2 choices. The first is to renting skis with $1 per day, or the second is to buying skis for $B. The skier has no idea on how many days to ski and needs to decide at the beginning of each day whether to rent or buy skis. The optimal deterministic online strategy is to rent for the previous B-1 days, then buy. It costs at most 2 times of the offline optimum. We adapt it to stragglers. Rent low-cost straggle strategies first, and buy a heavy solution only if slowdown persists. Our algorithm starts with S1, which is to ignore, and hope it is transient. Then we check cumulative slowdown. If slowdown is longer than S2, then we switch to S2. If the slowdown continues, we escalate to S3, and when the cumulative the slowdown is over S3's overhead, we use S4 as the last resort, which is to reschedule and restart. This balances effectiveness and cost dynamically without predicting the exact duration. Finally, we validate Greyhound in real-world performance. We answer 4 questions: how accurate is the detection, how effective is the mitigation, and what's the overhead, and finally, how does it scale? We tested Greyhound on NVIDIA H800 SuperPod with 400 GB InfiniBand, scaling up to 256 GPUs. We inject deterministic stragglers to a training job. We manually throttle GPU clocks and to inject computation stragglers and saturate network links with background traffic to inject communication stragglers. In terms of detection accuracy, our BOCD plus verification dominates. It achieves 100% accuracy and 0 false positive for computation stragglers. And for communication stragglers, it also achieves 99% accuracy. The overhead is only just 0.39%, which is negligible and cannot be distinguishable with inherent training fluctuations. Our method outperforms sliding window and raw BOCD on both accuracy and other metrics. We then evaluate mitigation effectiveness. We obtain that the macro batch adjustment strategy, or S2, reduces iteration time by up to 1.6 times for computation stragglers. And the optimization overhead is only within 30 seconds, even for more than 500 DP groups. The topology adjustment strategy, or S3, reduces slowdown by 1.23 times for congested links. And the overhead is 6.7 times lower than checkpoint and restart. For compound case that combines communication and computation stragglers, Greyhound coordinates S2 and S3 to limit the damage, and it finally falls back to restart after a long fail-slow period. We then evaluate Greyhound at scale. In large-scale training with 2,056 GPUs, we injected 12 stragglers. Greyhound shows 100% detection accuracy, and the average reaction time is only about 10 seconds. The mitigation is effective, and we can obtain that the throughput recovers rapidly after adjustments. Overall, Greyhound achieves 1.58 times higher end-to-end throughput versus the no mitigation case. This proves its effectiveness at production scale. To summarize, first, stragglers are critical. They are frequent, transient, and can cause over 34% average slowdown. Second, we present Greyhound Detect, which is non-intrusive, accurate, lightweight, and with negligible overhead. Third, we present Greyhound Mitigate, which is an adaptive multi-level strategy that balances cost and effectiveness. Together, they boost throughput by 1.58 times in large-scale training. We enable the efficient hyperscale training despite the imperfect infrastructure. Thank you.